It's working? Okay. You don't have to stand.
Okay, let's get started. I was asked to chair this session. Right? Absolutely. Okay. So the first talk will be by Andreas Metz, and he is also one of the conveners for the GPD week, the first week, and he's going to summarize, I guess, what has been discussed in that week, and also, in particular, on the topic of the generalized TMDs and Wigner description. Please.
So I will actually not give a summary of week one. This is something which I think today the conveners finalized, and this will be put on the key page. I was hoping that would have been done a little faster. Anyway, so I'm actually grateful to the organizers that they gave me the opportunity to talk about this topic here, generalized TMDs and Wigner functions. Generalized TMDs, we could also call them transverse momentum-dependent GTMDs. These are the type of objects for which we can at least hope that we can directly address them in experiment. On the other hand, Wigner functions are well known from non-relativistic quantum mechanics. They can be considered a quantum mechanical counterpart of a classical phase-space distribution. In Python structure studies, and I will come to that, we will see that these two types of quantities are related by a two-dimensional Fourier transform. So we did actually have 3 dedicated talks during the GPD week 1, on specific topics related, or subtopics related to this overarching topic. Mark Schlegel gave a talk on the definition of generalized TMDs, which is a non-trivial issue actually. Barbara Pasquini had the title Wigner functions and nucleon structure, and Feng gave a talk on observables for Platonic Wigner functions. I can only encourage everyone just to take a look at these talks. So here's just quickly the outline. I give a very brief introduction, then I say a few words about generalized TMDs, their definition, and I will also talk about the first application. Then Wigner functions, I will also go back to non-relativistic quantum mechanics to make the connection and to try to convey the message of why people are interested in these objects. And then the question, what can we learn from these objects? I call it applications of GTMDs and Wigner functions. And finally, observables, potential observables for these objects. So this is my entire introduction here. So it's basically from the EIC white paper. The white paper has this very nice graphic here, which contains the 2 of the currently discussed pillars of the EIC science case, the TMDs, parton distributions, which depend on the longitudinal and the transverse parton momentum. Then we have the impact parameter dependent distributions depending on the longitudinal parton momentum and the transverse position. It's well known that these objects through Fourier transform are related to GPDs. And then if we do suitable projections, we get down to normal parton distributions and various form factors. So in this graphic already highlighted is another type of function, Wigner functions, 5-dimensional objects depending on the longitudinal momentum, transverse momentum, and the transverse position. So while this is highlighted here in the graphic, not much text was spent on these objects. And this is basically all that you find in the document. It reads the impact parameter dependent distributions, and the TMDs give complementary information about partons, and those types of quantities can be thought of as descendants of Wigner distributions, W of x, B, T, K, T, which are used extensively in other branches of physics. I think this is a very important point. And then it finishes with, although there is no known way to measure Wigner distributions for quarks and gluons, they provide a unifying theoretical framework for different aspects of hadron structure we have discussed. That's it, text-wise. And I think it's fair to say, in the meantime, a few interesting things happened in this field. And I think related to the ongoing program here at the INT, the key question is, can Wigner functions or their Fourier transform GTMDs play an important role for the EIC science case? Not just in such a graphic, like we have an overarching tool, but we don't know how to get there. So this has two sub-questions. Number one, are they sufficiently interesting? Number two, perhaps even more importantly for the ESC candidate. And I try to present state-of-the-art in this area. So let me now start with some basic stuff here. I hope you bear with me here for a couple of minutes. Generalized TMDs and their definition. So this is a graphical representation of a GTMD correlator for quarks. I will use throughout this so-called symmetric frame, which is well known from GPT studies, where we use this average nucleon or hadron momentum as P plus P prime half, the momentum transfer delta P prime minus P, such that the momentum of the incoming nucleon is capital P minus delta over 2, and the outgoing is capital P plus delta over 2. The quark momenta are different here, and the average quark momentum is K. Now, in field theory, we define this object. We can define it through traces here. So we have a bilocal quark operator at the fixed light cone time, C plus equals 0. The quark fields depend on the C minus and the transverse position. We sandwich in a matrix gamma, which at least for leading twist selects a particular polarization of the quarks, and then we have also to worry about the negation. Now, this operator is evaluated now between different states. I just put momenta here, but you can actually add polarization labels and then detect the Fourier transform. As we'll see on the next slide, this is parameterized through a number of GTMDs, generalized TMDs, which depend on various arguments. Like for GPTs, we have a dependence on X, which is the average plus momentum of the two quarks, the longitudinal momentum transfer to the target, psi, transverse momentum transfer to the target, and on top of this, we keep the average transverse momentum. So what I have basically omitted here is two auxiliary scales, which you need for those objects. Like in the case of TMDs, it's at the same level of complexity. For these auxiliary scales, we have evolution equations. Experts know if you have such an operator which is not on the light cone, you run into issues with infamous light cone singularities. We know in principle how to deal with them. If you want to learn more about that, refer to this work. Now let's now take a look at parameterization of this object, and I confine myself to the chiral even leading twist quark GTMDs. So if we sandwich gamma plus between the two quark fields, means unpolarized quarks. And in that case, we find 4 GTMDs, which at the time we named F11 through F14. Likewise, for longitudinally polarized quarks, gamma plus, gamma 5, another 4 G11 through G14. So it's well known that if you look at the corresponding parameterizations for TMDs and GPTs, we have 2 functions only in each case. So you see already basically twice as many here. So if we look at all the leading twists, which means we have also to include the chiral odd sector, it's a total of 16. And later in the talk, I come back to this number. It's not accidental that it shows up. The same number of GTMDs appears for gluons. And to make it even more complicated, the GTMDs have both a real and an imaginary part. So what this means is we have actually a leading twist, we deal with 32 functions, compared to 8 leading twist GPTs and 8 leading twist TMDs. So I know very well, whenever you discuss something like that, there's immediately red flags coming up and stamp collecting. I have my personal attitude about that, so let me make a philosophical remark here. I think the community should not be afraid of collecting stamps. What I'm saying here not only applies to the GTMDs, where of course the number is kind of extreme, but sometimes when you talk about GPTs and TMDs, you get already accused of just collecting stamps. So I made this comparison the first time 4 years ago at the QCD town meeting, and I still stick to that. We have also in other fields of science many stamps. And if you think of the periodic table of elements, we have more stamps than we have here. I'm not even talking about isotopes. And no one would dare to say there's a certain element in the periodic table which we don't need, right? So the attitude, I think, which one can take here is, these are the stems that we find in nature, and I dare to say that nature is never bored. So I don't want to put myself in a defensive position if I show such a number. And so, but again, I know one can have different opinions about it. So
mosquitoes I can do without.
Sorry?
There are some mosquitoes I can do without.
This is true, but perhaps they also have a meaning.
Yes, probably the question is that if the number grows so much, how many of them are independent, or if there is a relation between them?
Well, I mean, I would say currently we have no indication that there's any relation. Like, at the same level, I mean, this discussion is at the same level as we talk about GTMDs and TMDs. I will actually briefly come back to this on the next slide. So let me now, we have seen that the Wigner functions are mother functions. We can also say the GTMDs, which are Fourier transforms, are mother functions. So I want to discuss that route here. So here I write again just the GTMD correlator. It's really the very same expression we saw a moment ago. And now I look here at the corresponding correlator for the TMDs. It's exactly the same operator which appears here. The only difference is that they evaluate this here between the same state. So in other words, I come from the GTMD correlator to the TMD correlator by putting the momentum transfer to the target to zero. That's one limit. Here's the corresponding correlator for GPDs. This is well known that this is a Lycone correlation function. So the transverse position of the quark fields is zero. But we can also get from this expression here right away to that by integrating over this average transverse momentum of the quarks. You can even follow me here in the argument if you're not familiar with that. The only K-perp dependence sitting in this expression is in the exponential. I carry this out, I get a delta function in C-perp, then I can integrate over C-perp, and this forces the two quark fields on the line. That's it. So all TMDs and GPDs are quote-unquote merely projections of these GTMDs. And I want to briefly talk here about the first application. This application was the reason why at the time, now about 10 years ago, we started looking in the classification of those objects. At that time, we were thinking quite a bit about the question, can there be any non-trivial relation between GPDs and TMDs? And the most famous one, which was put forward at that time, was between the GPD-E and the Sivers function F1T perp. We knew already that this relation can never have a model-independent status, but we wanted to make the argument as explicit as you could make it. And what you can do is, since the GPDs and TMDs are just projections, you can relate E and the Sivers function to the overarching GTMDs, and then you just see that they are projections of totally different functions. And this comes back to Marco's point. I mean, unless for whatever reason these GTMDs have some relation, I mean, this shows clearly there cannot be a model-independent relation of that. This is not the only case which is discussed. It's the most popular one, and it's actually discussed in various instances. And I go a little bit here off the script. Sometimes I get the impression that people forget that this is a model-dependent relation. In one instance where it is frequently quoted is when people try to explain the sign change of the Sivers effect between Sidis and Trillian. In such a simple picture here, which holds in lowest order, maybe I'm shouting too much, lowest order spectator models, you can relate this sign change to a difference between an attractive or repulsive force. But in general, you cannot explain it. So I'm not against this picture. All I'm saying here is when one talks about that, one has to keep in mind that this holds only in simple models at the quantitative level. Whenever you try to extract from this relation something quantitative, it gets very dangerous. And at present, we have no way to estimate reliably what the numerical difference is. So that's, I said a little bit more than I have written down. So let me finish this part by another incarnation of such a nice graphic from Marco Steele, kind of summarizing basically all the different objects that we use to characterize pattern structure of hadrons. So it's very similar to what we saw in the ERC white paper. We have the Wigner function, and the lower part is essentially the same. Here, the GTMDs have been added again. I come back to this. They are related to the Wigner functions through a Fourier transform. And he includes even another higher level here, what is called pattern correlation functions. These are functions that not only depend on the longitudinal pattern momentum, so the large light cone momentum and the transverse, but also on the small light cone momentum, the K minus. There's not many studies available in the literature on these objects, and it's probably relatively safe to predict that in the near future, not too much will happen here at this level.
And can you say how much related to double pattern distribution?
No. So
these are the ones that used to be called Fourier integration.
yeah, I mean, there is a relatively well-known paper by John Collins, Anastasia, and Ted Rogers talking about these objects and even the factorization, but I think this field never took off. So keeping in mind that I ignore this level, by the way, the counting of these functions is exactly as the counting after you integrate over K minus. So there's not new functions coming in. It's just you make a projection. So neglecting those, keeping that in mind, I think one can say GTMDs describe the most general two-pattern structure of hadrons. They definitely contain new physics, which goes beyond what we know from GTDs and TMDs. This not only is evident from the fact that GTDs and TMDs are just projections of the GTMDs, there's actually a whole bunch of these GTMDs which neither survive the TMD limit nor the GPT limit, and these may actually be the most interesting ones. So having this picture here, it may be desirable from a modeling point of view, rather than, for instance, having a separate model for TMDs and another model for GPTs or this impact parameter dependent distributions, to have a model for this Wigner functions, for instance. And then look at the various limits. It's needless to say that this is complicated, but this could be an important goal of pattern structure studies, and the same, of course, applies to measuring these agents. So let's now, I want to spend a couple of pages on this Wigner function. So introduced by Wigner in 1932, and I discussed this here just in non-relativistic quantum mechanics and make the notation as simple as possible in one dimension. They can be calculated from the wave function. So you have here a product of position space wave functions at different positions. Here's x minus x prime over 2, x plus x prime over 2. You integrate over this difference, the x prime variable, and you multiply also such a phase factor which contains the momentum. The outcome depends on x and k. This is what people define the Wigner function. That's Wigner. This should, of course, be fully symmetric between position and momentum space, and indeed you can readily verify that this expression here is equivalent to this expression where we use momentum space wave functions. Now, a nice feature is of the Wigner function, if, for instance, I integrate over the momentum, I get the density in position space. You can actually follow the argument. It's the same what we did before. If you integrate over k, the only k dependent sits in the exponent. Here you get the delta function in x prime. We integrate over x prime forces this x prime to 0, and you get the density. Likewise, if you integrate over x, you get the density in momentum space. And I think what really is a key equation here, why people get so interested in this object, or got so interested in this, even in non-relativistic quantum mechanics, is if you want to calculate an observable, you do it actually with a formula which looks exactly like you would calculate it if you have a classical phase-space distribution. You take the phase-space distribution, you multiply this your observable. This here is actually not an operator, it's really just a number, and you integrate over the entire phase space.
But then the left-hand side will not be a function of x.
Well, I call it I call it the expectation value of that operator, which depends on x.
No,
That's
so
just-
you cannot have the left-hand side dependent on x.
Well, this is just a piece of notation. I mean, what I say is I want to calculate the expectation value of this quantity. I think we are all on the same page. So again, this is, I think, what people like very much. Of course,
It's also, suppose O was the momentum.
sorry.
Suppose this operator O is just the momentum.
Yeah, you can also.
Then what would it look like on the right?
Yeah. Well, on the right-hand side, you would just put K. That's it. So you don't need to look at an observer which simultaneously depends on position and movement. So, and now a classical phase-space distribution by definition is positive, but this Wigner function can become negative, and this is due to quantum effects. So therefore, strictly speaking, we call such an object a quasi-proportionality. So one reason why people got interested in that is in order to understand maybe along a different route or get a deeper understanding between the transition from quantum to classical. All right, so let's now go to field theory and parton structure studies. So to the best of my knowledge, the first time this was discussed was by our chairman, G. and Belitsky in 2003. Let me actually look at one point here. This, of course, can be right away generalized to 3 dimensions, and then you have 6-dimensional phase space distribution. So what Feng and co-workers suggested in the first place in 2003 were 6-dimensional Wigner functions for parton structure studies. Then somewhat later, Cedric Losset, Barbara Pasquini came in and said, well, we can actually, in a relativistic many-body work with partons, we cannot resolve all the 3 spatial dimensions. We can only do the 2 transverse dimensions. So they advocated to look at the 5-dimensional object, which I think is now commonly used, dependent on x, longitudinal transverse momentum, and the transverse position. So this reduction from 6 to 5 is exactly the same what we got used to in the discussion of form factors. So non-relativistically, we take a bright frame, we have a 3-dimensional distribution, and people like 10 years ago argued, well, we can only do 2 dimensions. There's nothing different.
So why don't they like longitudinal coordinate?
Sorry?
Why don't they like longitudinal coordinate?
My understanding is that in such a situation with partons, I mean, we can never resolve the longitudinal position of the parton. If the experts may correct me.
You mean experimentally or theoretically?
Both.
No, theoretically in CGC, you need.
No, they say interpretation. Mainly it's because interpretation. If you keep longitudinal one, you only have a very defined interpretation in non-relativistic units. In relativistically, you cannot have any interpretation.
Why?
I only know it for the form factor. The form factor is because you boost the dynamics essentially start impacting each other.
Yeah, we basically create additional quark-antiquark pairs or whatever. So the folklore argument, which I normally hear about form factors as well, we have the old-fashioned definition, bright frame, it's 3-dimensional, and then we have the other definition in the infinite momentum frame, and the difference is somehow relativistic effects, which I understand includes parton production.
Well, certainly, I know in the case of small x, you can define them both. Of course, the distribution is not positive and has all sorts of problems with oscillations, but it's certainly definable.
The Wilson line.
You can't define it. It's just how you interpret it.
Yeah, okay, so you don't like them. So
No, it's not.
why in the transverse coordinate is it any better? Because your transverse variation
It's a-
size is
Yes, it's a boost invariance. So you can use the momentum, longitudinal momentum as one way to define your center of the nucleus.
That formula can work just based on the momentum.
space rapidities. Those are
Right, so you
Well,
have
the
to be
constant.
minus.
Yes,
You can
yes,
be
of
minus.
course, you definitely have X dependence there. I'm just saying that if you introduce the Z direction, the position, then the interpretation only have makes sense. I don't think the
generally
theory
the
is
most general thing would be to have transverse and then space-time momentum space rapidity.
you could have that.
So those
Yeah,
would
that-
be the most general.
Yeah.
But in general, you have the staple, right? The Wilson line.
Yeah.
Goes along the minus direction. So you're already integrating over x minus. And you're just choosing the endpoints to be at the same x minus. Whereas you can separate them and then you would have a b minus dependent as well. It will have a well-defined Lorentz properties.
Yes, you do.
In terms of interpretation, I have no idea.
So I think it's mainly interpretation. For example, one good example is mentioned that form factor. So only in the two-dimensional linear physical interpretation, if you really want to work three-dimensional interpretation, the charge distribution for example, Fourier transform form factor, that only work in the non-reduced unit.
But there's another class of problems which might be interested in this, and oftentimes in heavy ion collisions, you assume that momentum space rapidity and coordinate space rapidity are correlated, that they're equal, and in fact they aren't, they're spread out, and you'd like to know something about that spread. So it may be useful in other contexts, but
I mean, you can use that because here X definitely give you rapidity.
it doesn't tell you.
No. He's talking about x distribution versus b minus distribution. It's based on rapidity versus momentum rapidity.
So for massless particles, they're identical, but for massive particles, they're
Even for
Because
massless
you don't need it for what you're doing.
What?
Even
I'm just
for
saying there may
massless
be some
particles,
other
there's a
information
correlation
here.
here.
So
Oh yeah. I understand.
Maybe that's a good point actually for the discussion. So I just want to re-emphasize that this discussion here about, again, whether 5 or 6 dimensional is not something which is specific to these objects. It's really basically exactly the same discussion which people had like 10 years ago about form factors. So I want to be clear about that. So so we have a 5-dimensional object. Now we are in field theory, so we have a field operator. So we have 2 quark field operators at different positions. And let me go back to this page. So that formula on the other side page is the counterpart of this equation here. And now, of course, we have to sandwich here a gamma matrix to get a scalar and to worry about gauge invariance. And now people take this operator and just presenting what it's done. I mean, I was not an inventor of that. And evaluate it between hadron states that have the same plus momentum. So we put psi to 0, and we have just a transverse momentum transfer. And then you integrate over all transverse momenta, and you can readily show, actually by shifting this operator by amount of minus p per, you generate this exponential here. Then what you get here as a correlator is exactly the correlator of the GTMDs, which we talked about a moment ago. So the Wigner function correlator is a 2-dimensional Fourier transform of the GTMD correlator. And of course, you can invert that. Now, if you have these expressions here, it's not difficult to show that you can get the exact counterpart of these equations also. Namely, if we integrate over the transverse quark momentum, we get the density in longitudinal momentum and transverse position. If we integrate over E perp, we get the momentum density, the TMDs. And finally, we calculate also observable in this same manner. All right, so this, I think, is reasons why people in the first place got excited about that.
You said you got the field operators psi bar, right?
Yeah.
And then the states represent what? That you said using stuff.
So this is like, could think of nucleon, ion.
What are you integrating over?
The transverse momentum transfer to the state here. So let me now come to the point. So why do people like to discuss this? And I want to bring up 2 points. So the first, of course, is you can try now to do 5D imaging. And so here's a numerical example of such Wigner distribution. Actually, what is shown here is the Wigner distribution for unpolarized quarks in an unpolarized nucleon, the simplest case you can think of. Here for U quarks, here for D quarks, in a certain model, expression is integrated over all x, and in either case, we have a fixed transverse momentum of 300 MeV along the positive y direction. And then what is shown here is the situation in the impact parameter plane. So the first thing you notice comparing U and D quarks, the D quark distribution is wider than the U quark. This is nothing new or exciting. We already knew that from form factor studies. So let's now take a closer look at the shape. So you see that these distributions are actually not axially symmetric, but they're kind of squeezed or distorted. And this is due to the fact that we have a non-trivial dependence on the scalar product of k per dot b per. Now, to be a little more precise, you see that you have a top-bottom symmetry here. And this is due to the fact that actually you can show that this object is just an even function of that argument. In other words, an even function of the cosine of the relative angle between b per and p. This implies actually this top-bottom symmetry. And then, in fact, at least partly you can do that. The fact that the thing gets squeezed, you can kind of understand from intuition from confinement. So let me try to go through the argument. So let's say we look at quarks here along the y direction, like let's say 0.3 Fermi away from the center. And compare these two quarks, which are along the x direction, the same distance away, like 0.3 Fermi. Now, based on confinement, you would actually assume that the probability to find a quark which moves in that direction at this position here is less likely than finding it. Can you follow the argument? I mean, if
model doesn't have confinement.
Well, but it doesn't also deconfine, right? So, I mean, it describes a bound state.
Okay, so there is a bound state.
I mean, but having said this, there's of course a limitation to this explanation. If you think of quarks down here.
I don't understand your explanation. You're saying something which has momentum like this.
So the quarks have, all the quarks have a, I mean, it's just calculated in this way, momentum upwards.
Okay, and you're saying that is.
And then I'm saying, if I look at quarks, let's say at a certain distance away here along the y direction from the center, and the quarks move upwards, it's less likely, I mean, what this plot shows, it seems to be less likely than finding quarks at the same distance away from the center along the x direction.
I don't understand that. If something's moving in this direction, the potential, won't it move further this way than if that's no momentum?
Well, I mean, at some point it has to stop, right?
Yeah, but I mean, if you have a particle with small momentum that's going up the hill, it only goes a little way up the hill. When there's a big momentum, it goes up the hill, it goes a big way up the hill.
I mean, all the momentum for all the partons is the same. So this is really calculated. I mean, you could do a different calculation.
They have a momentum this way.
Yeah, so all the quarks here have a momentum upward.
Okay. So why doesn't a particle which has a momentum this way, it's a potential, go further up the potential than a particle which in the other direction has low momentum and will only go a little way up the hill? I mean, just think about a hill. If I have a ball, okay, and I'm at the bottom of the valley, I give a big momentum this direction, so it's further up the hill and have a larger spread than if I make it have a little momentum.
I mean, this still looks, at least on the top side, looks kind of intuitive to me. I mean, thinking a little bit, if I think of a fuzzy boundary of the nucleon, and I go to the extreme, to the boundary up here, really, let's say to the outer edge, I should not find quarks that actually keep moving in that direction and want to go outside.
They turn around, but they turn around at some distance, which involves some momentum. When the momentum is bigger, they turn around at a larger distance, and if the momentum is
Well,
But in that plot, you said all of them are fixed KT.
Yeah.
They all have the same
Yeah.
KT.
Yeah. So what's the model? What's
So
the
he's
physics?
looking at a
It's just
slice.
gauss-
so that's a light-cone constituent core model. I think we can, well,
I think you're talking about fixed modulus KT.
Yeah. And I mean, magnitude and direction is fixed.
Well, the magnitude and direction.
Yeah, but the direction is going up and down,
Yeah.
is what he said. And so,
No, it's just going all up.
yes, okay, yeah,
Yeah.
it's going up, okay, but that means that if the direction of momentum is in that direction, the physical spread, and that direction has to be bigger, and you have no momentum.
No, Larry, he's looking at a slice, which is that plot there is with a fixed slice corresponding to a fixed momentum and direction. So this is a plot in transfer space.
Yeah,
Right?
I
So it's a
understand.
plot in transfer space in which you've taken partons, all the partons have fixed momentum and direction. So it's purely a spatial plot.
Yeah.
So there's no question of motion with different things because he's taking a slice of the fixed.
I thought a classical distribution describes the distribution in space and momentum. So classically, what
He's taking a slice.
Yeah.
I understand he's taking a slice. That isn't the issue. The issue is that he's describing classical phase-space distribution in X and P. If P is bigger, I would expect that the typical spread in X is bigger.
Okay, this gets to another point.
Okay,
I really don't want
I don't
to
want
elaborate more on this.
That's some-
Anyway, I'm not too strongly advocating that here. I do find it appealing. I see actually, if you would go down here, it's symmetric, but the confinement argument would actually tell you that if the confinement is all, it should actually be bigger down. That's not the case. So here's one limitation of that. But anyway, I mean, still, I found it interesting, and there's a number of other cases where people look at polarization, where you can come up with a similar explanation, which seems to agree with intuition from confinement. That's all what I'm saying. Now, having said this, we should not forget that the objects can become negative. We know that from non-relativistic quantum mechanics, and there was an expectation that they also become negative in parton structure studies. This has actually been made explicit by Yoshitaka and Hagiwara. They take a simple quark target model. You look at the distribution of quarks in a quark and calculate that to lowest non-trivial order in perturbation theory. For fixed X, fixed transverse momentum, here the distribution given in E-perp, and here is a region where this object becomes negative. At that time, they actually proposed to go with another distribution, which is a Lucini distribution, which is known since 1940, also non-relativistic quantum mechanics. I don't present an equation here. The physics idea is you basically can start from the Wigner distribution, but you add the smearing, Gaussian smearing in K-perp and B-perp, and if you do it right, you actually can make sure, at least in non-relativistic quantum mechanics, that you get an object which is strictly positive definite or semi-definite. So you can also get zero. So they propose to work with this object. In field theory, there's an expectation that it's also positive definite. My understanding is that presently we don't have a formal proof. On the other hand, we don't have a counterexample either. One criticism that one can make is that because of the Gaussian smearing, the relation between the Lucini distribution and GTMDs and TMDs is less direct than what we have from the Wigner distribution. But that's, one could also go in more detail in the discussion about that. So to finish, I want to finish this discussion about attempts to get 5D images of hadrons with a couple of questions. Is there actually kind of optimal tool for this 5D imaging? And if we want to go with the Wigner functions, how could we actually interpret them if they are negative? Can we actually go beyond saying, oh, this is a clear quantum effect? And perhaps this is an area where we could learn from other fields, where they are used heavily, particularly in quantum optics. Now, the second application, I think this is the one which so far attracted most of the attention. It's a relation to parton orbital angular momentum, which appears in the spin sum rule. So if you take the concept of the Wigner function seriously, this is a natural way how you would calculate it. You take your Wigner function for longitudinally polarized, let's say, nucleon, unpolarized quarks, and you multiply with bperp dot kperp, and you integrate over the entire phase. That's it. And this is what was proposed in 2011 by Rosé Pasquini. Yoshitaka discussed in particular the gauge invariance of this way of defining the orbital angular momentum. One can actually show then relatively easily that this can also be expressed in this way. So one of the GTMDs, F14, which we have seen earlier. This is arguably the most intuitive definition of orbital angular momentum that we have in the field. A nice feature is that you can actually express both the Jeffrey-Manohar and the G orbital angular momentum, so the very same formula. The difference comes from the fact that in one case, you have to use the stable-like Wilson line to make the object color gauge invariant, the same stable that we use for TMDs, while for the G orbital angular momentum, you connect the two coordinates by a straight line. This definition has also been used by Matthias Burkhardt to get an intuitive interpretation of the difference between these two orbital angular momenta. I don't want to get into that. And it holds for gluons as well. Moreover, and I think one could give more arguments here, we can not only calculate the number, but with the Wigner functions, we have a chance in a very nice way to talk also about density of orbital angular. All right, so Yoshitaka already suggested in this paper that this could be used to calculate in particular the Jeffrey-Manohar orbital angular momentum on the lattice. And this is where we are with that. So Michael Engelhardt did first exploratory calculation of Jeffrey-Manohar orbital angular momentum u minus d quarks in lattice QC. So what is shown here in this plot is essentially the ratio of the Jeffrey-Manohar orbital angular momentum divided by the magnitude of the G orbital angular momentum. I should explain a little more here. This is as a function of a parameter which defines the length of the Wilson line, the stable-like Wilson line, which makes the operator gauge invariant. If this argument is 0, we get just the G orbital angular momentum and the ratio is 1. But in fact, since this is negative, we get -1. From a theoretical point of view, if you go with this to plus or minus infinity, you get the Jeffrey-Manohar orbital angular momentum. On the lattice, you cannot calculate to infinity, but fortunately, this saturates relatively quickly. And here, these values have been extracted basically as the Jeffrey-Manohar orbital angular momentum. And you see that the difference between the two is by no means negligible. So they find differences on the order of 30%.
Let's see, what's the difference between the G and the Jeffrey-Manohar?
You mean just theoretically?
Yeah, theoretically.
So the G, and loosely speaking, the G orbital angular momentum for quarks also includes a contribution which contains a gluon, because he works with a covariant derivative. And at least for a long time, the majority in the community was saying the Jeffrey-Manohar one is the more intuitive.
I see.
So I know there is still some discussion and some people think differently, but I don't want to get into that.
It's a question might be putting in interactions.
Yeah. So, but it's actually nice to see that this route with Wigner functions has been used to quantify for the first time the difference. And it's probably not exaggerating to say that all the developments in this area, Wigner functions related to orbital angular momentum, can be considered a milestone in high-energy spin physics. And just very quickly, one last application. This is like a more general discussion than just talking about the orbital angular momentum in a longitudinally polarized nucleon, namely spin-orbit correlations. And most of the work, again, was here done by Rosé and Pasquini. We are all familiar with this type of table, so this slide is actually taken from Barbara's talk in week 1. This tables where we have the quark polarization, unpolarized, longitudinal transverse, same for the nucleon, and then we put here in this table the 8 leading to its GTDs, likewise for the TMDs. Now, if you want to do the same game for the level of the Wigner distributions, where you have one transverse momentum more, and if in each field you want to have just one entry, then actually you should distinguish between transverse polarization X and Y direction. And then you see immediately you have 4 possibilities for the quark, 4 for the nucleon, 4 times 4 is 16, which is the number I have to stop. That's what it is. Okay. Yeah. So here we see again this number 16, just obtained in a totally different way. We went basically the hard route, going through all the Gordon identities, actually somewhat painful. So they appear kind of naturally. And another point, which from a physics point of view, I find really very exciting is using the GTMDs or the Wigner functions, we now for the first time can, in a true sense, speak about spin-orbit correlations. We have been doing this for years when talking about GPDs and TMDs, but for GPDs, you have only correlations that involve spin of the nucleon, spin of the parton, and position of the parton. While for TMDs, you have spin of the nucleon, spin of the parton, and the momentum of the parton. While a true spin-orbit correlation involves the orbital angular momentum of an object, and this is exactly what you can have if you have B perp and K perp. And I think this gives us actually an opportunity to quote-unquote communicate with other areas like AMO physics. So here we have 3 spin-orbit correlations. If we talk at this level, differential in B perp and K perp. So let me in the last few minutes now, these were the 3 points I wanted to emphasize concerning what do we know so far, what can we learn. And I will very quickly go through what do we know about the question, how can we measure it. So a very nice suggestion was made again by Feng, Yoshitaka, and Owen Zhao 2.5 years ago, that they suggested to look at diffractive exclusive back-to-back dijet production, leptonucleon and leptonucleus collisions. This is a sketch of the process, so you're exclusive here on this side, you know the kinematics of the virtual photon, you say, let me measure the 2 jets, and then you can readily verify that you have that you are sensitive not only to the longitudinal momenta of these gluons, but in particular to the transverse. This, of course, there's a question, and to what extent or how precisely can I measure, in particular, the transverse momentum of jets? And I don't know, Elke could perhaps comment on that. I know you are doing or have been doing quite a few studies on that. People also argued that if you include here target polarization, longitudinal target polarization, there may be a way to get a handle on this F14 gluon. In other words, the gluon orbital angular momentum in the spirit of Jeffy-Mann. The natural kind of extension was put forward by Yoshitaka and co-workers. Just let's do the same thing in ultra-peripheral PA or AA collisions, where you use the photon flux provided by a heavy nucleus, which could be explored in the LHC and RIC. Then this is all about gluons. What about quarks? Something that we put forward like last year was on the one hand simple, but on the other hand complicated process, an exclusive double Trillian process, which we did here with pion nucleon induced. And now we look at 2 dilepton pairs and the final state nucleon. Leading order, you have 2 graphs here, and you have twice an annihilation of quark antiquark into a time-like virtual photon, which then indicates into a dilepton pair. Again, you can readily show that you're sensitive in principle, particularly to the transverse parton momenta. Here, in leading order, one is only sensitive to the so-called orbital region, where these objects here describe the emission of a quark antiquark pair. This, I think, is probably something which at present may be a showstopper. There's a low count rate, the amplitude is proportional to the fine structure Compton squared. This is like double deep virtual Compton scattering. And here the general question related to ERC is, can one somehow measure quark GTMDs in leptonucleon and leptonucleus collisions? We don't know at this point. We actually wanted to follow up here on this idea and come up with a process that has a little bit a larger count rate. This we did more recently, looking at exclusive double production of eta B or eta C, nucleon scattering, where we have here twice an annihilation of two gluons into eta C or eta B. It's basically the same topology that we had for the double trillion. The count rate is larger because it's strong interaction, but now we have gluons in the game, and the question here is, can this be measured? I learned that eta C's have been seen. At the LHC, there's even has been measured PP to PP and 2 J psi. I am not aware that people have identified this final state. So the eta C or eta B is relatively complicated compared to J psi. A nice follow-up work here, again by the two gentlemen here in the room and co-workers, is to exploit double parton scattering. I don't have an extra plot, but you can actually understand from this plot what happens. Just imagine that you don't look here at the exclusive final state, but that the nucleon breaks up. So you have here in the upper part, nucleon going to two gluons and X. And this is like exactly a double parton scattering situation. I think you will have a larger count rate. Experimentally, it will be easier because you don't have to detect that. On the theoretical side, there may be some additional complications because you have one additional particular transverse moment. But again, for EIC, this is all there. So
if it's exclusive, then you also have to worry about survival.
Yeah, so that is definitely an issue here. So if you cannot quantify that, one thing that one could think of is, for instance, look at ratios. Let's say it's looking at a certain azimuthal correlation from the I mean, what one has to understand that it's not too long ago that there were many people, first of all, nothing was known. And no process was known how they can be measured. So this is really all kind of exploratory, saying, at least theoretically, we have now identified a few processes, exclusive processes, that are sensitive to the transverse parton moment. I'm not saying that I'm happy with the state of the art, but that's basically it. So strictly speaking, yes, there's factors.
But I mean, if you do this calculation, say, PA, small x, and as inclusive, you'd still be sensitive to unintegrated gluon distributions. You have this small x. These are KT dependent objects. This calculation 15 years ago.
So maybe we can. This is really direct
but
sensitivity, but not in the sense model dependent sensitivity.
Okay, but there's a gap that I'm really concerned about. Okay.
So yeah, I think for the sake of the time, I should summarize. So the GTMDs, partonic Wigner functions, have attracted considerable interest. Several interesting applications have been identified. I want to emphasize this point here. I think that Wigner functions can bring parton structure studies to the next level. They contain more information than GTMDs and TMDs, less information than the wave function. In non-relativistic quantum mechanics, knowing the wave function of the Wigner distribution is basically equivalent. Here, in a many-body relativistic theory, this is different, but we know that the concept of the wave function has its limitations in our field. So if we can get somehow to the next step, this is a viable candidate. The other thing I want to emphasize is in other areas, people make a dedicated effort to somehow extract Wigner functions. In our field, if we find the right process, we get them for free. So we just have to find processes, an exclusive process that is sensitive to the transverse momentum of the parton. So we should try to take advantage of this situation. Of course, there's many questions. Can one learn even more about the physics content of the Wigner functions or related distributions? Very important, I think, can one measure at all quad GTMDs and leptonucleon and leptonucleus collisions relevant for the EIC? Right now, the most promising process for EIC and gluon GTMDs that has been put forward is dijet production. And is there other processes in leptonuclear and leptonucleus that are sensitive to GTMDs? That's it.
Thank you, Andreas. We already had many questions, but we still.
So instead of double, you have to see about chi-C.
Of the rate?
No, you have to see it's very difficult. So you press G by C.
Could.
Can I ask potentially a stupid question? If you go back to your processes to measure gluon GTMD, not gluon core, so we see eta-C or eta
Which one?
production. Yes, this one is.
So that would be gluons.
Okay, and for quarks it was the double trillion and the direct. Okay, then my question is clear. I somehow misunderstood that the eta-C was also for quarks, but that all is clear. I'm sorry, I just misunderstood.
I have one question. So the GPDs, you always have the issue that in reality it's difficult to really measure, because you say you measure you have to more or less go to theory friends and find out where it is your reform. Do the GTMDs have the same issue? Well, directly measured, or is it the same that more is I gotta go hand in hand?
In fact, this is it's actually I'm glad that you bring that up. I mean, you're referring to the deconvolution problem. Right?
Yeah.
If you analyze this process or this here at leading order, if you measure your final state kinematics, you can actually pin down X. I mean, Feng and Yoshitaka should speak for that here. For this here, I know for sure. So if we look at the specific kinematics in the final state, X is fixed. And the only variable which is integrated over is K perp, and you have a constraint basically. You have one independent K perp integration. Okay. But you can actually pin down X. That is actually nice.
But B curve also needs to
Sorry?
B curve.
P probably is easy. K probably is
B curve is just doing the Fourier transform.
yes.
Okay, I mean that complication. I mean this goes beyond the deconvolution because of the X. Yeah.
So we all model then the spin off with the K per D curve. That's a big push too, in my view, that you can directly pin your kinematics down and measure it rather than trying to deconvolute.
Yeah. No, so one could put it differently. One could actually put it differently. If you're just interested in GPDs, maybe, well, again, this process here is probably right now academic because no one can measure that. But if you have another similar process, one may actually look at a situation where you have the transverse momentum dependence in the first place, but X is fixed, and then, well, you have to make some assumption how the transverse momentum is, and you integrate over it. But you may actually, this type of processes may actually help you. This is a qualitative state, it's not quantitative. May help you to learn something about the X distribution of GPDs.
There is a whole
Yeah.
grail.
Yeah.
I mean, it's just beginning, I think. We need more.
Yeah.
No, we definitely have to.
I always go back to the old transversity. First, you guys asked us to measure also only digets. The very first transversity they were dihedrons and digets. Isn't it? Yeah. And then we started going beyond that. Very first transversity was digets.
Okay.
So my guess is it's going to be experimentally very, very difficult, even for a long time. So you essentially have to measure K perp and DT more or less at the same time.
So, I mean,
So
yeah, what
there you're trying to measure K perp and B from the final state proton, and then you want to measure K perp from the jets. That's going to be
so you have basically with sufficient accuracy to pin down the kinematics of all your final states.
But one comment though.
The imbalance, the KP in our work
Yeah.
balance, we have already shown in some. So now you need a detector which has enough acceptance that you have also the proton, which at the moment STAR has an issue with. But for the rest, the digits is not so challenging. Yeah, no, okay. I don't want to be negative. At JLab, I think the digit is not.
But we can certainly do a feasibility study of error. We can't. So I looked into it once, and I can't. The problem is that there's no data sample with both the proton tag, which is a good T measurement, so that we can actually measure the, and you know. But what we can do is we can do a feasibility study, like a rapidity cut, get the final state,
So
look at the digits and see if we can actually measure this thing.
If we can just continue that on a little bit. I lately have really kind of seen the moment something is happening with me. Ilka was at Brookhaven to visit Yoshi and me, and Christian 8, they implement now UPC, and he has already had the first results where we can actually use UPC, get the digits, and get the proton forward, and actually to see what luminosity we need. And funny enough, we have the data set on tape. We just need to start analyzing.
Yeah, so in fact, for Hera data, we can start this relatively easy. So I need somebody.
Okay, so
people.
so I want I want comment on this actually. We have been thinking about this. So at the beginning, I talked to Ernst and Eka on this, and at that time, I indeed wanted to really measure recoil of the proton. Right. But recently, discussing with Yushitaka and also many other people say that now maybe we can do actually just look at the digit. So the sense that if we understand the QCD correction for the digit production process, maybe we don't have to look for the recoil. And we were still in the process of trying to digest this.
So there is in fact a digit, diffractive digit production paper by H1, I believe, that actually exists. Yeah, there is data. Yeah. Right.
You have, of course, in order to really kind of narrow down your kinematics, you have to really have a string kind of kinematic constraint. So we can talk.
So how do you make sure that it's really? I mean, you still have to make sure that it's exclusive.
Yes, so that's actually a very good question. So you have to make sure that the total transverse momentum of the digit is very small, and you're dominated by the diffractive process.
Yes.
So you limit yourself in the digit, the total transverse momentum is very small, and then you're looking for those events, and then you can identify the diffractive process.
So in fact, I think they actually tag the proton.
I mean, if you can tag the proton, you can actually cross it.
Yeah, so I believe there's enough.
Yeah, so I personally think if you have a design like we are talking about EIC to tag the proton, is not such a big deal anymore. I think it's more the rate of diffractive digits and then your detectors that you can measure your TPT imbalance. I think that is the potentially. And then, okay, you were not here as I talked about, were you maybe about the TMD, because we did this with the gluon TMDs. The biggest issue is actually you're smearing due to harmonization in the chat. That you need to unfold this. I don't think that the problem lies in measuring the proton. The problem lies in unfolding the harmonization effects on your chats. Yeah. So we published this paper just not too long ago on this, and I think that is actually the bigger challenge than the proton.
And it's only the these guys make a lot of progress here. We're in good shape.
Exactly.
So Eddie, what would you say that the transverse momentum resolution with which you can measure
That
jets.
depends really on your detector. But even without detector, if I just can finish my sentence, I have shown this how much the asymmetry from parton level gets smeared if you look to your your jet, and the biggest effects are actually the harmonization for jets. So that you don't, that your jet is not a parton. At the end, it's particles which you kind of combine in your jet algorithm, and we studied not various jet algorithms, which study different radii, and that makes no difference. I haven't looked in different jet algorithms.
But I think that can be handled.
I agree.
It's a QCD effect. So
Exactly.
also,
You can do, but I think that is a bigger effect than this proton, or more, yeah.
So you could definitely then use this also for really genuine TMD physics.
Yeah.
If you look in DIS at hadrons
Oh,
inside the jet,
so the
then
operator asked
you
me
can measure
to.
cleanly the TMD fragmentation.
Okay, I think that we should defer this into discussion. Okay, sorry, I didn't control it.
No.
Okay, so let's take a address